When I talk about black holes, thermodynamics, and entropy, I am really talking about the deep connection between gravity, information, and the fate of the universe. In this monologue, I want to walk through what we know, how we know it, and where the open questions are, especially where black holes meet dark matter, dark energy, and cosmic expansion. I will keep the language simple, but I will not dilute the physics. I will start from something familiar: thermodynamics. In everyday physics, thermodynamics is about heat, energy, and entropy. Entropy is a measure of how many microscopic configurations correspond to the same macroscopic state. A hot cup of coffee has many more ways its molecules can be arranged than a perfectly ordered crystal at absolute zero. So we say the hot coffee has higher entropy. The second law of thermodynamics says that for an isolated system, entropy never decreases. It can stay the same in ideal cases, but in practice it increases. This is not a moral rule. It is a statistical fact about systems with many degrees of freedom. Now, gravity enters this story in a surprising way. If I have a gas in a box and I let it evolve, it spreads out. Entropy goes up as the gas fills the volume. But if I have matter in space under its own gravity, it does the opposite. It clumps. Galaxies form, stars form, planets form. At first glance, it looks like gravity makes things more ordered. Matter that was spread out becomes concentrated. That seems like entropy is going down. But that is not the right way to count entropy in a gravitational system. To see why, think of a cloud of gas collapsing under gravity to form a star. The gas loses gravitational potential energy as it falls inward. That energy is radiated away as light and heat. The radiation goes out into space and increases the entropy of the surroundings. The star itself is more ordered than the original diffuse cloud, but the universe as a whole has gained entropy. The entropy is carried off by the photons. So the second law is safe. Gravity does not break thermodynamics. It just shifts where the entropy lives. Black holes are the extreme end of gravitational collapse. If you compress enough mass into a small enough region, the escape velocity exceeds the speed of light. You get an event horizon, a boundary beyond which nothing can return to the outside universe. Classically, in general relativity, a black hole is very simple. It is described by just a few parameters: mass, spin, and electric charge. This is the content of the no-hair theorems. All the detailed information about what fell in seems to be lost behind the horizon. From the outside, you cannot tell if the black hole formed from a star, a cloud of gas, or a pile of dark matter. Only the total mass, spin, and charge matter. This simplicity creates a puzzle. Imagine I have a box of gas with some entropy. I compress it into a black hole. If the black hole has no entropy, then I have taken a high-entropy system and turned it into an object with basically no internal degrees of freedom, at least from the outside view. That would mean entropy decreased. That would violate the second law. So something is wrong with the idea that a black hole has zero entropy. In the early 1970s, Jacob Bekenstein took this seriously. He proposed that black holes must have entropy, and that this entropy is proportional to the area of the event horizon, not the volume. That was a radical idea. In normal systems, entropy scales with volume, because the number of microscopic degrees of freedom usually grows with the amount of stuff you have. Bekenstein argued that when matter falls into a black hole, the entropy of the outside universe decreases, but the area of the horizon increases, and that increase in horizon area should be interpreted as an increase in black hole entropy. If you add the entropy outside plus the entropy of all black holes, the total never goes down. This is the generalized second law. Stephen Hawking then made a crucial step. He used quantum field theory in curved spacetime to study what happens near a black hole horizon. He found that black holes are not perfectly black. They emit thermal radiation, now called Hawking radiation, with a temperature that depends on their mass. The smaller the black hole, the hotter it is. The Hawking temperature is inversely proportional to the mass. For a black hole with the mass of the Sun, the temperature is tiny, around 10 to 7 Kelvin, far colder than the cosmic microwave background. So astrophysical black holes today are effectively colder than their surroundings and absorb more radiation than they emit. But in principle, in a cold enough universe, they would radiate and slowly evaporate. Hawking's calculation did more than predict radiation. It also fixed the constant of proportionality in Bekenstein's entropy formula. The entropy of a black hole is given by the Bekenstein-Hawking formula. S equals kBA for 4Lp², where A is the area of the horizon, Kb is Boltzmann's constant, and Lp is the Planck length. The key point is that the entropy is proportional to the area of the horizon in Planck units. That is an enormous number. A black hole with the mass of the Sun has an entropy on the order of 1077 in units of Kb. Supermassive black holes in galactic centers have entropies around 10 to 90 or more. They dominate the entropy budget of the present-day universe. This area scaling is one of the deepest clues we have about quantum gravity. It suggests that the fundamental degrees of freedom of spacetime are not distributed throughout the volume, but are somehow associated with surfaces, with horizons. This idea evolved into what we call the holographic principle. The rough statement is that the maximum amount of information in a region of space is proportional to the area of its boundary, not its volume. It is as if the physics inside a region can be encoded on its boundary, like a hologram. This is not a metaphor. It is a concrete statement about the counting of states in quantum gravity, supported by calculation string theory and by the behavior of black holes. Now I want to connect this to the large-scale universe, to dark matter, dark energy, and cosmic expansion. Our universe on large scales is well described by general relativity, plus a few energy components: ordinary matter, dark matter, radiation, and dark energy. Dark matter behaves like a pressureless fluid. It clusters under gravity and forms the backbone of large-scale structure. Dark energy, on the other hand, has negative pressure and drives the accelerated expansion of the universe. Observations of distant supernovae, the cosmic microwave background, and galaxy clustering all support this picture. About 5% of the energy density is ordinary matter, about 25% is dark matter, and about 70% is dark energy, if we describe dark energy as a cosmological constant. In a universe filled with matter and radiation, structure forms. Small density perturbations grow under gravity. Regions slightly denser than average pull in more matter. This process creates galaxies, clusters, and eventually superclusters. Dark matter plays a central role here. It does not interact with light, but it interacts gravitationally. It forms halos that host galaxies. Over cosmic time, as matter collapses into these structures, black holes form at the centers of galaxies. Many galaxies host supermassive black holes with masses from millions to billions of solar masses. These black holes grow by accreting gas, stars, and possibly dark matter, and by merging with other black holes. From a thermodynamic point of view, this is a process of entropy production. When gas falls into a galactic potential well, or into a black hole, gravitational potential energy is converted into heat and radiation. That radiation increases the entropy of the universe. When a black hole grows, its horizon area increases, and so its entropy increases. If I sum up the entropy in all black holes, plus the entropy in radiation and ordinary matter, I get a total that increases with time. The second law holds on cosmic scales. What about dark matter and dark energy? Dark matter contributes to gravitational collapse and structure formation, so indirectly it feeds black holes. But we do not yet know if dark matter itself has any special thermodynamic behavior beyond that of a cold, collisionless component. We can assign an entropy to dark matter if we think of it as a gas of particles, but that entropy is much smaller than the entropy in black holes. Dark energy is more subtle. If dark energy is a true cosmological constant, it is like a uniform energy density filling space with a fixed value. A universe dominated by a cosmological constant approaches a de Sitter spacetime. A de Sitter universe has its own horizon, called the cosmological horizon. Observers see a horizon beyond which they cannot receive signals. That horizon has an associated temperature and entropy, very much like a black hole horizon. The entropy of a de Sitter horizon is also proportional to its area. In our universe, if dark energy is a cosmological constant, the de Sitter entropy is finite and huge, much larger than the entropy of all black holes combined. This means that as the universe expands and becomes more and more dominated by dark energy, there is an ultimate limit to how much entropy can be contained in the observable region. Black holes that form and grow now are adding entropy, but the total possible entropy is bounded by the de Sitter horizon entropy. So we have at least 3 important entropy reservoirs in cosmology: the entropy in radiation and ordinary matter, the entropy in black holes, and the entropy associated with the cosmological horizon if dark energy is a cosmological constant. Right now, black holes dominate the entropy budget of the matter sector. In the far future, if the universe approaches de Sitter space, the horizon entropy will dominate. Now I want to talk about the fate of black holes and the fate of the universe in thermodynamic terms. In the standard picture, the universe keeps expanding. Dark energy drives accelerated expansion. Galaxies not gravitationally bound to us move beyond our horizon. Star formation slows as gas is used up. Over trillions of years, stars die and stellar remnants cool. Black holes remain as the main dense objects. Over even longer timescales, black holes themselves lose mass by Hawking radiation. They evaporate. A stellar mass black hole takes around 1067 years to evaporate. A supermassive black hole with 1 billion solar masses takes around 10 to 100 years. These timescales are unimaginably long compared to the current age of the universe, which is about 10 years. When a black hole evaporates, it converts its mass into radiation. The Hawking radiation is thermal, at least in the semi-classical calculation. That radiation spreads out through the expanding universe. Entropy increases during evaporation because the radiation has many possible microstates. However, there is a tension here. If the black hole started from some pure quantum state, and Hawking radiation is perfectly thermal, then information about the initial state seems to be lost. The final state is mixed. This is the black hole information paradox. It is a conflict between quantum mechanics, which says that evolution is unitary and information is preserved, and the semi-classical picture of black hole evaporation, which suggests information is destroyed. Most physicists think that in the full theory of quantum gravity, information is not lost. The consensus is that Hawking's original calculation is incomplete. The radiation is not exactly thermal. It carries subtle correlations that encode the information about what fell in. But we do not yet have a complete, universally accepted description of how this works in general spacetime backgrounds. In certain special cases, like in anti-de Sitter space with a dual conformal field theory, we can show that black hole evaporation is unitary using the ADS-CFT correspondence. This is a concrete realization of the holographic principle, but our real universe is not anti-de Sitter. It is closer to de Sitter because of dark energy. We do not yet have a full holographic dual description of de Sitter space. So there is still a gap between the models we can solve and the universe we observe. Still, we can say something about the thermodynamic arrow of time. The second law tells us that the total entropy of the universe, including black holes and horizons, increases. It does not tell us why the universe started in a low entropy state. That is a separate puzzle. The early universe, shortly after the Big Bang, was hot and dense, but in terms of gravitational degrees of freedom, it was very smooth. A nearly uniform distribution of matter and radiation has low gravitational entropy because there are many more ways for matter to be clumped into black holes and structures than to be smooth. Over time, the universe evolved from that smooth, low gravitational entropy state into a clumpy, high entropy state with galaxies, stars, and black holes. The growth of structure and the formation of black holes is the main way gravitational entropy increases. Dark matter plays a key role here. It seeds the gravitational wells that lead to galaxy and black hole formation. Without dark matter, structure formation would be slower and less efficient. The universe might still form some structures, but the timeline and the amount of clumping would be different. So dark matter indirectly drives the production of gravitational entropy. It is like a scaffold for entropy growth. Dark energy, on the other hand, eventually shuts down structure formation. As accelerated expansion takes over, regions of the universe become causally disconnected. New large-scale structures stop forming. Existing structures become isolated island universes. Black holes in those islands will continue to exist and eventually evaporate, but the overall pattern is that the universe moves toward a state where almost nothing happens on large scales. This is sometimes called the heat death, a state of maximum entropy where no free energy is available to do work. However, in a universe with a cosmological constant, the asymptotic state is not just a uniform bath of low-energy photons. It is a de Sitter space with a horizon and a finite temperature. The de Sitter horizon emits thermal radiation, analogous to Hawking radiation from black holes. So even in the far future, there is a kind of thermal activity associated with the horizon. But from the point of view of any observer, the universe looks like an empty space with a small temperature, with no new structure forming and no large gradients to exploit. It is interesting to compare the entropy of black holes to the entropy of the cosmological horizon. For our current dark energy density, the de Sitter horizon radius is about 16 billion light-years in comoving coordinates, and the associated entropy is around 10 to 122 in units of kb. That is vastly larger than the entropy of all black holes in the observable universe, which is around 10 to 103 to 10 to 104. So in the long run, if dark energy is constant, the dominant entropy is in the horizon itself, not in the matter content. The universe is then limited by a kind of holographic bound. The maximum entropy inside our horizon is finite and set by the horizon area. This brings me back to the holographic principle. Black hole thermodynamics taught us that the entropy of a region with a horizon scales with area, not volume. In ADS-CFT, we have a concrete realization of holography. A gravity theory in a bulk spacetime is equivalent to a non-gravitational quantum field theory on its boundary. In that context, black hole entropy can be counted by counting states in the boundary theory. But for a universe like ours, with positive cosmological constant, we do not yet have a complete holographic dual. There are proposals, but no consensus. We also do not fully understand how to count the micros corresponding to the de Sitter horizon entropy. For some special supersymmetric black holes in string theory, we can count microstates and match the Bekenstein-Hawking entropy. That is strong evidence that the area law is counting real quantum degrees of freedom. For de Sitter space, we do not yet have that level of control. There is another open question. How does dark energy itself fit into a thermodynamic and microscopic picture? If dark energy is a cosmological constant, it is just a fixed parameter in Einstein's equations. Its energy density is constant in time and space. But quantum field theory suggests that vacuum energy should be enormous, much larger than what we observe. The fact that the observed dark energy density is small but non-zero is the cosmological constant problem. We do not know why the vacuum energy takes the value it does. We also do not know if dark energy is truly constant or if it changes slowly with time, as in models of dynamical dark energy. If it changes, the future thermodynamic fate of the universe could be different. For example, if dark energy grows with time, we could end up in a big rip scenario where structures are torn apart. If it decays, the universe could eventually stop accelerating and even recollapse. Each of these possibilities would change the long-term behavior of horizons, black holes, and entropy. Even within the standard picture, where dark energy is a cosmological constant, there are puzzles. In a de Sitter universe, the horizon entropy is finite. That suggests that the total number of independent quantum states accessible to an observer is finite. That is very different from the usual infinite-dimensional Hilbert spaces we use in quantum field theory. How exactly to define quantum gravity in a finite-dimensional Hilbert space and how to reconcile that with local physics is not fully understood. At the level of black holes themselves, we also have unresolved issues. We know that black holes have entropy proportional to area. We know they have temperature and radiate. We have strong theoretical reasons to believe that information is preserved in their formation and evaporation. But we do not yet have a universally accepted detailed mechanism that works in all situations. Proposals like firewalls, fuzzballs, and soft hair try to resolve the tension between quantum mechanics and the smoothness of the horizon predicted by general relativity. Each of these proposals changes something about our picture of spacetime near the horizon. None has been definitively confirmed or ruled out. We also do not know how dark matter behaves very close to black holes. Does it form dense spikes around them? Does it annihilate or decay and produce observable signals? Does it have any special coupling to gravity beyond the standard model? Observationally, we see the gravitational effects of dark matter on galaxy scales and larger. Near black holes, baryonic matter dominates the observable signals. So the detailed thermodynamics of dark matter in strong gravity is still an open area of research. Finally, there is the question of initial conditions. We can describe how entropy grows from the early universe to now, and we can project forward to the far future. But we do not yet understand why the universe started in a state with such low gravitational entropy. The early universe was nearly homogeneous with tiny fluctuations. That smoothness is what allowed structure to form and entropy to grow. Inflationary cosmology explains how a small patch of space can be stretched to become our observable universe, smoothing out inhomogeneities. But inflation itself raises questions about initial conditions and entropy. Did inflation start in a low entropy state? Does it produce universes in a multiverse? And if so, how do we define entropy there? These questions are not settled, so we have a coherent thermodynamic story that links black holes, horizons, dark matter, dark energy, and cosmic expansion. Black holes are thermal objects with entropy proportional to area. Their formation and growth are major channels for entropy increase in the universe. Dark matter helps build the structures that feed black holes. Dark energy shapes the large-scale geometry and sets a horizon with its own entropy and temperature. The universe seems to be heading toward a state where black holes evaporate and a de Sitter horizon dominates, with a finite maximum entropy. But at the same time, we are missing key pieces of the microscopic picture. We do not fully understand the quantum degrees of freedom that give rise to black hole and horizon entropy. We do not know how information is encoded in Hawking radiation in a realistic, expanding universe. We do not know why the cosmological constant has the value it does. And we do not know why the universe began in such a low entropy state. All of these questions sit at the intersection of gravity, quantum theory, and cosmology. They are not philosophical in the sense. They are precise technical questions about how space-time, matter, and information behave. For now, black hole thermodynamics gives us a powerful set of clues. It tells us that gravity has a deep thermodynamic and informational side. It tells us that horizons carry entropy and temperature. It tells us that the ultimate fate of the universe is constrained by these thermodynamic laws, but it does not yet tell us the full microscopic story. One of the most concrete open problems is this. In a universe like ours with dark energy and an apparent de Sitter future, what is the exact quantum description of the horizon degrees of freedom that account for the de Sitter entropy? And how do they connect to the information stored in black holes that form and evaporate within that horizon?